Hey guys, we're going to work on the Unit 6 review. I know on the paper it says Unit 7, but it's really Unit 6. Okay? So the first two questions are just transformation questions. So it gives us, be very careful and look at what it gives us. It gives us a function negative 3 raised to the x. So this is an exponential function that already has the negative involved. So then there are two more transformations that were added, okay? But we do not include the negative because it was already there, okay? So first off, we have a positive 5 right here, so that means up 5. So up 5. And then we have a negative x. So we had a positive x. Now we have a negative x. What does that mean? It means a reflection across the y-axis, all right? It's a reflection across the y-axis. I'm going to say that's ray because I'm too lazy to write it all out. Okay, so that's it. Okay, so this one's tricky, all right? This one over here is a tricky question. All right, so we have the natural log of x changes to the natural log of x cubed. Okay, think about it for a second. When we think of the power property of logs, if I wanted to, how could I move this 3? That's right, I can move it out to the front and make it 3 natural log of x. Why do I mention this? Because now I can say, what does this 3 tell me transformation-wise? That's right, it's a vertical stretch by 3. Okay? Since we were able to move that 3 from being in a power position to being just multiplying to the function, all right, I know that's a vertical stretch by 3. All right, last transformation question, number 3. We have log base 5 of x, and it's changed to 5 raised to the x. We went from a log to an exponential. So this is a reflection across the y equals x line. Not the y-axis, but across the line y equals x. So it's a reflection across the line y equals x because we inversed it. We went from log to exponential, and those two are inverses of one another. And so it's a reflection across the line y equals x. All right, let's move on. Number 4. It wants us to expand. Okay, so first off, we have a fraction. So that means I'm going to be able to break this up into 2 logs. And the numerator minus the denominator. Okay, so they each get their own logs. But now I have to look inside the logs and see if there's not more I can do. Well, this log has a square root, and we know square root is the same thing as raising to the 1/2 power. So we say 1/2 natural log of x minus. Okay, now this guy has 2 things multiplying inside, so they're going to get their own logs, and this minus sign is going to distribute, otherwise it would be a plus sign right here, and it's going to be, and the power is going to move out front. Natural log of x. And bam, we're done. Remember, this right here, instead of being a plus right here, was a minus because this minus sign would go to this entire log. So when I expand it, if you had wanted to, you could have put parentheses and a plus sign in between, and then distribute the negative sign. They both get negative, okay? All right, this one says to condense. Okay, remember guys, basically here's the thought. If it's positive, it goes in the numerator. If it's negative, it goes in the denominator. So this 2 can move in and become a power. This 4 can move in and become a power, and this 2 can move in and become a power. So we get log base 8. Now, we have a positive a squared over b to the 4th. And then this, where does this c squared go? Well, it's positive, so it goes in the numerator. Okay, let's move on. Number 6, determine the domain of the natural log of x minus 2. Guys, you should remember that a log graph has a vertical asymptote at x equals 0. Okay. But this minus 2 means I shift the graph to the right 2. So now we don't have it at x equals 0 anymore. Now we actually have our vertical asymptote at x equals 2. And so my graph looks something like this. So I can say then it's from 2 to infinity, but I never actually touch 2. So I make sure I put a parentheses around the 2. All right. Next question. Determine the range of 2 raised to the x minus 3 plus 4. So this is exponential. You should remember that exponential graph has a horizontal asymptote at y equals 0. Now that's the parent function. Except I move this graph up 4 and right 3. Now moving up 4 does not affect your horizontal asymptote. Okay? So now I have an asymptote here at y equals 4. And so my graph looks something like this. So then my range would just be from 4 to infinity. All right. Let's move on. Number 8. Let Q represent a mass in grams of carbon-14 whose half-life is 5,715 years. The quantity present after t years is given by that equation. Determine the initial quantity when t equals 0. It's just 15. It's just, this number, you guys remember, represents the beginning amount of something. So it's just 15. All right? Determine the quantity present after 4,000 years. Okay, this is a very easy problem. It just wants you to plug in 4,000 for t. That's all this problem's looking for. So, pull up my handy dandy calculator. So I'm going to say 15 times 0.5, the same thing as 1/2, raised to the 4,000 divided by 5715. Press enter, and I get 9.23. So the quantity present after 4,000 years is approximately 9.23 grams. That's approximately that. All right. So that was pretty simple. Moving on. Let me know, if that's something that doesn't make sense. Number 9. Using the model from question 8, generate a new function m to represent the mass in grams of the material with a half-life 29 years and initial mass 17. Guys, all I want you to do is, their half-life is 5715. I want a new function where my half-life is just 29. Their initial amount was 15. I want a new function where 17 is the initial amount. So you could just say 17 times 1/2 t divided by 29. Bam, that's all she wants. That's all she wrote. That's what I meant to say. Okay? Next problem. Stop. I don't know why it's being weird like this. Okay. The rate of ventilation required in a public school classroom depends on the volume of airspace per child. Use this model where y is the rate of ventilation and x is the cubic feet of airspace per child to approximate the required rate of ventilation in a room with 350 cubic feet of airspace per child. Guys, x is the cubic feet of airspace. It wants me to find the rate of ventilation, so that's y. They've given me a formula. Just plug it in. So I can just say 76.8 minus 11 times the natural... I never got 11. 11 times the natural log of 350. I press enter, and I get 12.36. So that is the rate of ventilation. Approximately 12.36. All right? The rate of ventilation is approximately 12.36. All right? All you have to do is plug it in. Plug it in and go. All right? Next problem. Real quickly, just like I pointed out to you guys the first time we did this problem, you need to change the second hundred to 1,000. All right. Again, if you don't actually ever read this, then it doesn't really affect anything. But if you do read this, the formula won't make sense. So what you need to do is change the second 100 to 1,000. Okay. What is the population after 5 months? T is measured in months. What do? Plug in 5 for t. This is just a calculator situation. So we're just going to say 1,000 divided by, okay, now I have to put mine in parentheses because I can't do the alpha y equals thing y'all can do. 9 second e raised to the, need to put this in parentheses too, negative 0.1656 times 5. And I get 202.75. That is the population. Now, that answer doesn't make sense, right? Because this is talking about animals. So I can't say 0.75. That's stupid. So how many animals would I have? 202. Okay. Next problem. At 8:30 a.m., a coroner was called... Sorry about that. At 8:30 a.m., a coroner was called back to the home of a person who had died during the night. To the home, not back. To the home of a person who had died during the night. In order to estimate the time of death, the coroner took the person's temperature twice. At 9 a.m., the temperature was 85.7, and at 11 a.m., the temperature was 82.8. The temperature of the room was a steady 70 degrees. Solving for time in Newton's law of cooling, we get that T equals that formula, where T is the time in hours since the person died, and T is capital T is the temperature in degrees Fahrenheit of the person's body. When did the person die? Guys, there's some extra information hidden in this problem. Okay? Information you don't technically need. Alright? So, sorry, I was trying to think of the best way to explain it. They gave you two different body formulas. Two different body temperatures, sorry. He measured it twice. The problem is look at our new formula. Do I actually need to measure it twice in order to find T? No, there's not like, I don't want you guys to confuse this with a project we've been doing. See, in the project, we did not give you the constant. In this situation, the -10 constant is given, all right? You don't have to worry about finding it. See, in the project, you actually had to go find K. We not only already gave you K for this formula, we also already rearranged the formula to solve for T, so you don't have to worry about solving for T, all right? We've made this, it's not like the project. It's similar to the project, but it's not like the project, okay? In this situation, all you need to do is pick one of the two measurements. So like, let's use 85.7. So we're going to say that time, little t, is equal to -10 times the natural log of 85.7 minus 70 over 98.6 minus 70. And this is going to tell us how long he's been dead since we took his temperature, the 85.7 temperature. Okay? So, we're going to say -10 times the natural log. Now, I have to open a ton of parentheses here. Divided by 98.6 minus 70. Close. Okay, press enter. And we get that it's basically 6 hours, like 5.997. So if you were to take this 7 and round this 9 up, it would round that up, which would round that up. So it's been 6 hours since he died. Now, when did I take this temperature of 85.7? Well, I took this temperature of 85.7 at 9 a.m. Okay? So when did the person die? Well, 6 hours prior to 9 a.m., which would be 3 a.m. So he died at 3 a.m. And you could do the same thing if you want to use the other formula. You would get the other temperature, my apologies. You would get the same answer. So let me show you that real fast. You do not need to do it twice. Guys, I can only repeat that so many times. You do not need to do it twice, okay? But I'm just trying to show you that if I was to use the other temperature as well, I would get that he died 8 hours ago. And if you work back 8 hours from not 9 a.m. now, but 11 a.m., because that's when that was taken, you would once again get 3 a.m. All right, so they both work. Okay? All right, let's move on. This thing's being a pain. All right, 13. Consider these four functions. Which one has the following function as the property as, y approaches 0 as x goes to infinity. So in other words, guys, it's just saying which one of these, as we go to the right, y is going to be getting closer to 0. Okay? Like infinitely closer to 0. Okay. I could say, oh, you should just graph all these by hand, but none of y'all are going to do that. And so since we're just kind of gearing up for a test, let me show you just kind of a shortcut way. My suggestion, just graph each and every one of these on your calculator. So we hit graph for this one. Okay, as we look to the right, so in other words, remember it says y is going to 0 as x goes to infinity. So as we look to the right, is my y value getting closer and closer to 0 for this graph? Yes, it is. So it seems that the first one is good. So I'm just going to say number 1 because I don't feel like rewriting it. All right. Now, that doesn't mean that's the only one that does that. I still have another 3 functions. So we should check them. Okay. 2 raised to the x minus 5. Okay. As I go to the right, is my y value getting closer and closer to 0? No, that one doesn't work, right? Okay. Let's look at this next one. -4 plus log of x. Let's hit graph. As I go to the right, is this guy getting closer and closer to 0? Well, no. Because you should remember that a log graph will continue to rise the more right I go. So eventually it's going to be well past 0. It's going to take a long time to get there. I shouldn't have gone to this. It's going to take a long time to get there, but eventually it's going to be all the way up in the thousands. All right? So no, that one does not do it because it continues to pass 0. Okay? It continues past 0. All right? So then my last graph is the natural log of negative x. Hit graph. Okay, so once again, as we look to the right, is y approaching 0. As I look to the right, is y approaching 0. Well, which way is y headed here? It's headed down. Is that y approaching 0? No, y is not approaching 0 at all. Okay, so the only answer for part A is number 1. Part B, which of the following functions has the property that y goes to negative infinity as x approaches 0? So now we're looking at x approaching a specific value, 0. Now, where is x 0? That's important to remember. Where is x 0? All up and down the y-axis. Okay? So basically we're saying as we approach the y-axis, what is y doing? Okay? So we look at, let's just look at this last one. Natural log of negative x. Remember, this is where x is 0. So where does this graph approach an x value of 0? Well, right here, right? As we get closer and closer to it, what is the y value doing? It's going down. So this would be approaching negative infinity. So this function does fit the bill. I don't feel like writing it, so I'm just going to say number 4. Okay? Now, that doesn't mean it's the only one that fits the bill. Let's look at a couple others. Negative 4 plus log of x. We hit graph. Okay, remember, we just care about y approaching 0. I mean, x approaching 0, and what is y approaching negative infinity? Well, look here. The graph approaches an x value of 0 right here, and it's going to continue going down because it's a log graph, right? So we know that log graphs come from an asymptote and shoot out, right? So it's going to continue going down forever. So the third one fits the bill as well. Okay? Alright, so now let's look at the second one. I'm just working my way backwards. 2 raised to the x minus 5. Oh, I need to put this in parentheses. X minus 5. Hit graph. Okay, remember, what is y doing as we approach an x value of 0? Well, this graph is a exponential graph, so we have a horizontal asymptote right here. Is there any way for this guy to approach negative infinity on the range if there's a horizontal asymptote? No. If there's a horizontal asymptote, guys, like let's pretend there's a horizontal asymptote right here across the x-axis, I cannot approach negative infinity if I can't go past this horizontal asymptote. Alright? So number 2 does not fit the bill. Now let's look at number 1. Alright, which is negative e raised to the negative x. Hit graph. Alright, again, as x approaches 0, which is all right here, what is y doing? Well, as x gets to 0, that happens right here, and y is like negative 1 or something. That's not approaching negative infinity, so that one's not the answer either. So 4 and 3 both fit the bill for part B. Alright, I know it's a little confusing. You might want to watch that part again and just kind of think through it. Alright, let's go down. I don't know why it's not letting me scroll down so easily. Alright, solve for x. Okay, so when we look at 14, x is trapped inside the log. Alright, so that means I first have to get the log by itself, the natural log, and then I will change from log form to exponential form. So I subtract 2 on both sides. So I get 3 natural log of x equals 6. Divide both sides by 3, and I get the natural log of x is equal to 2. So now I want to change form. So what's the understood base for natural log? E. So I say e, take this number, it becomes your power, e squared equals x. And you should be able to at least go to your calculator and approximate it. I could ask you either form for the test. Alright, so you should be able to go to your calculator and approximate and see that 7 point, oh, let's just round to the thousands, 389. So x is approximately 7.389. Alright, let's move on. Number 15, sorry. 3 raised to the x equal to 1 over 81. Okay, so it's important to realize that this is an exponential function. So that means I need to get the base that has the variable exponent by itself first. Then I change forms. Well, my base with the variable exponent is 3 because it's 3 raised to the x. It's already by itself, so I can start off changing forms. So I change from exponential to log, the same base. That becomes your input, and your exponent becomes your equals, so equals x. So now I can just type this in my calculator. Remember, you can use your log base ability in your calculator. You hit math, you scroll up till you see log base. I do not have that ability, so I have to do it through what's called a change of base formula. Okay. Press enter, and I get -4. So x equals -4. All right, last but not least is number 16. Now look, we have 2 variables for number 16. But what was the instructions to solve for x? That means we need to get x by itself. So I'm going to move everything to one side and get x by itself. So we have 3 plus log x equals y. So x is trapped by the log. So first I have to solve for the log. So I subtract 3 from both sides. Now, I can't actually subtract y and 3. That doesn't give me anything, so I just leave it as y minus 3. Now, what is the understood base if you have log x? That's right, it's 10. So I'm going to say 10 raised to the y minus 3 equals x. And bam, I've solved for x. I got x by itself. Okay, that's all she wrote. Alright guys, I know this video went long, but I was trying to take my time and explain everything. Please let me know if you have any questions. Alright, thanks. Have a great day.